Hello students, today we will see time response of second order system. In last lecture we have discussed about the time response of first order system. We have studied the output response by applying different inputs. Okay. Now we will discuss about the time response of second order system. So look at this. See here. Here the block diagram for second order system is given. Okay. When I am saying second order, so highest power of s in denominator, that is characteristic equation, will be the denominator of the transfer function. Okay. See, this is called as the standard form for second order system. Here this form is with different parameters. I told you here omega n term is there. Omega n is natural frequency of oscillation. Okay, so unit will be definitely radian per second. Here zeta term is there. Zeta is called as damping. We will see the effect of zeta also. Okay, how it is affecting on the output. Then see, if this is the block diagram, we know that this is g of s and h of s is equal to unity. Okay, so to get transfer function, we will do g of s upon 1 plus g of s into h of s. See here, I have substituted value of g of s. I have substituted here also, as negative feedback system is there, so there will be positive sign, h of s will be 1. Okay. Now what I did here, c of s upon r of s. Okay, I have rearranged and I got this transfer function. So see, you have to remember this transfer function, because this transfer function we need while calculating or solving the numericals. Okay. So the standard form you have to remember, omega n square upon s square plus 2 zeta omega ns plus omega n square. Okay. So you have to remember. So if the characteristic equation of second order system is as, so standard characteristic equation for second order system, denominator of the transfer function. So that is s square plus 2 zeta omega ns plus omega n square. Okay. So this is standard form. If any system is given and we need to compare that system with the standard one, so you have to remember this characteristic equation. Okay. Again I am repeating, what is standard characteristic equation? S square plus 2 zeta omega ns plus omega n square equal to 0. Okay. Now see, just now I told you that we will discuss about the effect of zeta on the output response. What is zeta? Zeta is called as a damping ratio. Okay. So what I will do, I have this characteristic equation. So order of this characteristic equation is 2. So that is second order system. So what I will do, I will find the roots of this characteristic equation. As order is 2, so there will be 2 roots. Okay. So that 2 roots I have shown with S1 and S2. So we know this formula, minus b plus minus under root of b square minus 4ac upon 2a. Okay. So we will compare and see here a is equal to 1 and this is in the form of ax square plus bx plus c. Okay. So I have just compared and I have calculated abc from this characteristic equation. I have substituted here and I got the roots as, look at the roots, minus zeta omega n upon, plus minus j omega n under root of 1 minus zeta square. See, you can calculate by substituting the value here, you will get the same answer. Please cross check. So these are the roots here. Now what I did here, minus zeta omega n, you can check that here there is a negative real part. Okay. See, we have studied that S is equal to sigma plus j omega. Okay. In S domain, what is S? Sigma plus j omega. So sigma is real part, j omega is imaginary part. So same is the thing here, but here real part is negative and this part is imaginary part. Okay. Now what I will do here, look at this, omega n under root of 1 minus zeta square, I can substitute, I can replace this with omega d. Okay. Because omega n is natural frequency of oscillation and omega d is called as a damped frequency of oscillation. What is omega d? Omega d is nothing but omega d is equal to omega n under root of 1 minus zeta square. So we got the formula for omega d. Omega d is equal to, again I am repeating, omega n under root of 1 minus zeta square. So look at this. Here I have written the roots S1 comma S2. I have replaced that term with the omega d term. Okay. So I got roots here, minus zeta omega n plus minus j omega d. Okay. Omega d, again I am repeating, damped frequency of oscillation. So why we have calculated these roots? Because we have to check the effect of zeta on the output response. So what is zeta? Zeta is called as the damping ratio. Okay. See, I will write here zeta is damping ratio. So what I will do, I will substitute different values of zeta here. Look at this. I have substituted different values of zeta. Okay. So what I will do, I will put zeta here. I will calculate number of roots. I will put that roots. That roots will be nothing but the poles. Okay. Because this is nothing but the roots of characteristic equation. And we know that when you will compare characteristic equation with 0, so you will get number of poles. Okay. So we need to substitute that poles in S domain and we will check the output response. So see, we will check one by one. Now remember, S1 comma S2 I have minus zeta omega n plus minus j omega d. So first of all I will consider zeta is equal to 0. Means damping will be 0. No dampings are there in the system. So when zeta is equal to 0, look at this. This real part will be 0. Real part will be 0 and there will be only imaginary part. Okay. So what I will do here, S1 comma S2 is equal to plus minus j omega d. Okay. So this is plus minus j omega d. So what I am getting, real part is 0 and I am getting the imaginary part. Okay. So I will put these imaginary roots. But how the roots are there? Plus minus j omega d. So what I will do, look at this, plus minus j omega d I have substituted. And we have studied this in stability concept also. If the roots are located on j omega axis, we know that if the roots are located on j omega axis, system will be marginally stable. Okay. So marginally stable means it is not stable nor not unstable. Okay. So it is on the verge of stability and instability. So how we are getting output response for that? We know that we are getting oscillations. And that oscillations are called as sustained oscillation. You can check here. Your output is continuously changing, but this is within the margin. Okay. It is not increasing, not decreasing. This is within the margin. So again I will repeat, when damping is 0, when no dampings are there, in that case we are getting the output response like this, that is called as sustained oscillation. So it is just like the marginal stability. Okay. Now see, now I am changing or varying zeta. So now I have considered this zeta in the range of 0 to 1. See, I have considered this zeta as a positive value, but this zeta is in the range of 0 to 1. Okay. So when zeta is in the range of 0 to 1, same roots I will get. So what you will say to those roots? These roots are having negative real part as well as there will be the complex part, that is imaginary part. So look at this. What I will say, I am getting complex conjugate roots. What I am getting? Complex conjugate roots. Okay. So this part is real part, this part is imaginary part. I will locate that two roots in S domain. So I have substituted these roots here. Look at this, minus zeta omega n is actually the real part. Okay. So it is just like minus 2, just imagine, minus 2 plus minus 3j suppose. Okay. So I have substituted that roots and these roots are called as complex conjugate. Okay. So see here, real part is negative. So roots are located on left hand side of j omega axis, and we have studied that when roots are located on left hand side of j omega axis, system will be stable. Okay. But see, when there are oscillations, or what I will say, when the zeta is changing, so there are some disturbance. We have studied that initially the response will be the transient response, and after some time the transient will die out and we will get a steady state response. So look at this carefully. Such type of response is called as underdamped response, and you will get underdamped response only when the zeta is in the range of 0 to 1. Okay. Next we will see for zeta is equal to 1. What you need to do? Substitute here zeta is equal to 1. So what I will get here, look at this. This omega d is nothing but omega n under root of 1 minus zeta square. Okay. So if I will put zeta is equal to 1 here, so this term will be 1 minus 1 0. So what I will get here? Only minus omega n. But you can check here, S1 will be minus omega n and S2 will be minus omega n. So there will be two roots with same negative real part. Okay, same negative real part. So see, I have shown here overlapping roots. Okay. So when such type of thing is there, that is overlapping negative roots. So how I am getting the response? You can check. Here we are not getting transients. Okay. But initially the output response is increasing and it will get settled after some time. So such type of response is called as critical response or critical damping response. Okay. So when zeta is equal to 1, that response is called as critical response. Okay. Now next, I will consider the value for zeta greater than 1. Okay. So when I am saying zeta greater than 1, look at this. Zeta greater than 1. So this term, you can check that this part will be negative part. Okay. So again j into j, that will get cancelled out. So what I will get here, minus zeta omega and plus minus omega under root of zeta square minus 1. I have just written here. Okay. So from this you can conclude that here I am getting two roots. Okay. Because this part will be minus zeta omega and plus this part. Second root will be minus zeta omega and minus this part. So you can check that when zeta is greater than 1, I am getting two roots, but that two roots will be different. In previous case, when zeta is equal to 1, roots are same. Okay. But here roots are negative real part, but that two roots are different. Okay. So look at this. Here I have located that roots in S domain, S1, S2. So what you will comment on the stability, roots are located on left hand side of j omega axis. So definitely system will be stable. Okay. But if we have to show with the output response, so look at this. Here you can check that here I am getting the output response like this. If you will compare these two response. So look at this. Here initially it is increasing suddenly and then it will get settled as fast as with this overdamp system. But here you can check that here this is somewhat lagging as compared to this critical response and this will get settled like this. Okay. So if zeta is greater than 1, then this response is called as overdamp response. Okay. So in short, we will conclude now. If we are varying the value of zeta, what is zeta? Zeta is called as damping. So it is affecting on the output response and definitely it will affect on the stability of the system also. So how we will select the value of zeta? So look at this. Here I have drawn the graph, or this graph is nothing but for the output response. On y-axis I have taken c of t, on x-axis is t. Okay. So this graph is nothing but the addition of these four outputs. Okay. So we can see that we have concluded if the value of zeta is in the range of 0 to 1, that response is called as underdamped response. Okay. And we need an underdamped response because transient response will be for small duration and after that it will get settled out to get steady state response. So this is desirable response. Okay. And we have seen that if this zeta is decreased, look at this. Here I have shown the response. If zeta is equal to 0.2, so you can check the amplitude, initial amplitude is large. If zeta is increased to 0.6, so this amplitude is decreasing. So we know that if the amplitude is more, so it will require more time to get settled. If the amplitude is less, so it will get settled as fast as previous one. Next, if zeta is equal to 1, you can check that here this overshoot is not there. We are not getting the increase in the amplitude if zeta is equal to 1 or the greater than 1. Look at this. Here zeta is equal to 1, here zeta is equal to 2. Okay. So what is desirable value? Desirable value of zeta, it should be within 0 to 1. That is called as underdamped response. Okay. So I hope you got the concept of